Hello there, and welcome to the DODO SCIENTISTRY. I'm glad you've chosen to spend a few quiet moments with me tonight. Wherever you are, in a cozy bed, a hammock under the stars, or perhaps lying on the couch with a cat on your chest, I hope this gentle journey into the atom will help you unwind, breathe a little slower, and let your thoughts float softly into sleep. Before we begin, I have a small favor to ask. If you enjoy these peaceful science rambles, a like and a subscribe really help the channel. And it's completely free, like stargazing or daydreaming about quantum foam. And I'd love to know, where in the world are you listening from tonight? Maybe let me know your local time too. It's always fascinating to see this little sleepy community stretch across the globe, like a quiet constellation of curious minds. Now, I do hope this video doesn't turn out to be too interesting. You see, it's a fine balance. If you do end up staying awake until the end, well, at least you'll know a lot more about atoms than when you started. And if you drift off somewhere around the discovery of electrons, that's perfectly fine too. Either way, we're in no rush. This episode is all about whispers. Specifically, the soft, persistent whispers of the atom. From ancient Greek philosophers dreaming up invisible particles to the modern dance of quantum mechanics and subatomic chaos, we're going to ease through more than 2,000 years of ideas, experiments, surprises, and occasional explosions. But don't worry, tonight, there will be no lab coats, no tests, and no alarms. Just curiosity and calm. So let's take a deep breath, settle in, and follow the trail of tiny things. Things too small to see, yet somehow holding up the entire universe. And as always, this video is for relaxation and educational purposes only. It is not intended to be medical advice or a substitute for professional care. His rejection of the void meant that the idea of atoms floating through empty space had little traction. And because Aristotle's works were so influential, especially once adopted by medieval scholars, the atomic idea was largely shelved in favor of more continuous, qualitative models of matter. Add to that the philosophical discomfort with imagining invisible particles, and atoms found themselves exiled from respectable thought. But even as atomic theory lay dormant, something important was happening quietly in the wings. People were starting to sort and classify substances. Alchemists and early natural philosophers began documenting the properties of different metals, minerals, and acids. They observed how substances reacted, combined, and changed color. Though they lacked a unifying theory like atomic structure, they were gathering data, sometimes messily, often poetically, but data nonetheless. In the Islamic Golden Age, scholars such as Jabir ibn Hayyan, often Latinized as Jeber, advanced alchemical practice by systematizing it. Jabir is credited with developing early forms of distillation, crystallization, and evaporation. He believed that all metals were composed of different proportions of mercury and sulfur, a theory that wasn't quite right, but edged closer to the notion that different materials have distinct internal structures. Later, in the European Renaissance, alchemists like Paracelsus brought their own flair to the field. Paracelsus introduced the idea that chemistry could be used to treat disease, shifting the focus from gold-making to medicine. He also expanded the elemental system by introducing salt as a third principle, alongside sulfur and mercury. Not the table variety, but a symbolic essence of solidity and fixity. Alchemy was growing more complex, with its own language, rituals, and an increasingly experimental attitude, though still wrapped in mystery. Despite the mystical overtones, these early practitioners were developing lab techniques and chemical processes that would eventually prove invaluable. Glassware evolved. Reactions were cataloged. Mixtures were separated. The idea of transformation was being explored, not just symbolically but practically. In the East, Chinese alchemy had its own rich history, often tied to Taoist philosophy and the search for immortality. Practitioners worked with cinnabar, mercury, and other substances believed to grant longevity or enlightenment. Although the spiritual goals differed, Chinese alchemists also observed chemical reactions and changes in matter, contributing to the broader human understanding of material transformation. So, while the atomic model gathered dust, the world didn't stand still. Through hands-on work, accidental discoveries, and the occasional philosophical detour, People were gradually assembling a patchwork understanding of substances and how they behave. The atom wasn't yet back in the spotlight, but the stage was being quietly set. Looking back, it's easy to smile at the idea of lead turning into gold, or elixirs granting eternal life. But within those ambitious dreams was a deeper yearning to understand the fundamental nature of matter and life. Alchemists believed that the world held secrets and that through careful observation, symbolic reasoning, and maybe a little luck, those secrets could be unlocked. In their way, they were listening for whispers too, just not yet from atoms. But to understand how radical that was, it helps to appreciate the scientific mess he inherited. At the time, one of the dominant theories about combustion, how things burn, was the phlogiston theory. According to this idea, every combustible material contained a mysterious substance called phlogiston. When something burned, it was thought to release its phlogiston into the air. A flame, therefore, wasn't a chemical reaction. It was just phlogiston leaving the building. There were some problems with this theory. For instance, certain metals gained mass when burned, rather than losing it, which was odd if phlogiston was supposed to be escaping. But instead of ditching the theory, many tried to explain this away by suggesting that phlogiston had negative weight. Yes, negative weight, like an invisible balloon hiding in your coal. Lavoisier didn't buy it. He had a different approach, one rooted in experimentation and relentless accuracy. He believed that the only way to understand a chemical reaction was to know exactly what went in and exactly what came out.
No guesswork. No metaphysical fall.
So he built himself a laboratory. Not just any lab. It was the scientific equivalent of a grand ballroom, filled with polished copper instruments, balances sensitive enough to detect the difference in a single grain of sand, sealed glass vessels, and elaborate gas collection setups. He spared no expense, which was convenient, since he was also a wealthy tax collector. His wife, Mary Ann, was a brilliant collaborator who not only illustrated his experiments, but also translated scientific papers from English to French and helped edit his work. If you've ever imagined chemistry as the grimy pursuit of beakers in a dungeon, Lavoisier's gleaming lab would have felt like a breath of fresh, measured air. One of his most important discoveries came from studying combustion more closely than anyone before him. He observed that when a metal like mercury was heated in air, it formed a calx, a powdery substance that we now know is an oxide. But here's the twist. The calx weighed more than the original metal. Instead of assuming that phlogiston had vanished, Lavoisier suspected that something had joined with the metal. Using closed vessels and carefully controlled air volumes, he demonstrated that a portion of the air was consumed during the process. That missing portion, he realized, wasn't a void or a loss. It was oxygen binding to the metal. From this, he formulated one of the most important principles in all of science, the law of conservation of mass. In a chemical reaction, matter is neither created nor destroyed. It only changes form. Burn a log, and it might turn to ash and gas. But if you capture everything, the smoke, the soot, the leftover carbon, the total mass remains the same. This might sound obvious today, but at the time, it was revolutionary. The idea that chemical processes followed precise rules and could be accounted for down to the milligram was a major leap forward. Lavoisier's insistence on measurement did more than just tidy up a few theories. It changed the way chemistry was done. Before him, many reactions were described qualitatively. This powder smells sweet. That one turns blue. This mixture gets warm. Lavoisier pushed for a quantitative approach. How much heat? How much weight? How much gas? Chemistry began to shift from a descriptive art to a mathematical science. Instead of swirling symbols and esoteric labels, Lavoisier called for a new language based on observable facts. And he didn't stop at oxygen. Lavoisier was instrumental in identifying and naming several key elements. He helped establish the modern understanding of hydrogen and nitrogen and played a central role in compiling the first systematic list of elements. Gone were the days of earth, air, fire, and water. Now there were real substances, each with measurable properties and predictable behaviors. In 1790, He published the Traité élémentaire de chimie, the elementary treatise of chemistry, which many consider the first modern chemistry textbook. It introduced a systematic chemical nomenclature and clearly outlined chemical reactions using equations. It's hard to overstate how much this book changed the game. For the first time, chemistry students could learn from a structured, logical system, rather than being handed a mysterious collection of symbols and recipes. He also coined the term oxygen, from the Greek meaning acid former, based on his, ultimately incorrect, belief that all acids contained oxygen. Not every guess was perfect, but his overall method, observe, measure, repeat, was solid gold. There's a poetic irony to Lavoisier's life. While he brought order and reason to the science of matter, the world around him was descending into chaos. The French Revolution was gathering steam, and Lavoisier's role as a tax collector made him a target. Despite his scientific fame, he was arrested and sentenced to death. In 1794, at the age of 50, he was executed by guillotine. The mathematician Joseph Louis Lagrange remarked afterward, "It took them only an instant to cut off that head, and 100 years may not suffice to produce another like it." Lavoisier's death was a tragic loss to science, but his work endured. His approach set the stage for generations of chemists to come. The laboratory became a place of precision, not potions. Reactions were balanced like equations. Substances were named, classified, and tested. Matter had rules, and those rules could be learned, tested, and taught. Most importantly, he gave us confidence that the physical world could be understood through careful observation, that you could weigh air, count invisible gases, and find order in the flicker of a flame. Through his experiments, matter began to feel real in a way it hadn't before. Not just the stuff of dreams or elements, but measurable, quantifiable, knowable. Lavoisier didn't invent the atom, but he carved a path straight toward it, by insisting that every chemical process followed the same laws. No matter how dramatic or subtle, he helped lay the intellectual foundation for seeing matter as a system of parts and patterns. The world under his lens wasn't magic. It was math in motion, in the glow of his laboratory lamps, weighed on brass scales and sealed in glass. The chemistry of the future had quietly begun. Turns out, atoms can be split, and isotopes mean not all atoms of an element are truly identical. But for the early 19th century, this was a stunningly useful model. It made chemistry predictive, not just descriptive. Dalton's work didn't just explain what chemists were already observing. It gave them a way to organize it. By assigning weights to atoms and identifying how they combined, he laid the groundwork for something extraordinary, a deeper classification of elements. Soon, other chemists began to adopt and refine his ideas. They improved the accuracy of atomic weights, developed better techniques for isolating elements, and started noticing patterns. Certain elements had similar properties. Some reacted the same way. Others seemed to repeat at regular intervals when listed by mass. The periodic nature of elements was slowly coming into focus. Dalton didn't live to see the full emergence of the periodic table, but his atomic theory lit the path that led to it. By giving atoms distinct identities, he transformed chemistry from a messy collection of recipes into a rational science. Elements became more than just names in bottles. They were defined by their atomic character, their weight, their bonds. It's worth noting that Dalton wasn't a celebrity in his time. He never held a prestigious academic post. He kept teaching at a small Quaker school in Manchester and continued his meteorological observations until the end of his life. But his ideas quietly reshaped the world. Today, every chemistry student learns about atomic weights, molecular ratios, and Dalton's laws of proportion. They may not know that he also studied colorblindness, now sometimes called Daltonism, or that he was terribly fond of long walks, but they know his dots. His little atomic sketches launched a revolution, not with a bang, but with a scribble. Perhaps the most charming thing about Dalton was his devotion to logic. He didn't invent atoms because it was fashionable. In fact, most scientists at the time still preferred more fluid theories of matter. But Dalton, armed with his experimental results and a stubborn sense of reason, followed where the numbers led. If matter behaved in consistent ratios, there had to be a reason. If different elements combined in simple whole numbers, there had to be a pattern. And that pattern, he believed, was made of atoms. The power of his theory lay in its simplicity. It explained chemical reactions without needing mysterious forces or hidden fluids. It treated substances like puzzles made from tiny parts, parts that you could count, weigh, and rearrange. For the first time, matter wasn't just observed. It was modeled. It had structure. It had math. Dalton's world was still one of hand-blown glassware and flickering lamps. There were no electron microscopes, no lasers, no particle accelerators. But even without seeing atoms, he showed us how to think about them. His ideas were clear enough to hold, small enough to picture, and solid enough to build on. And so, thanks to a quiet teacher with a sharp pencil and a sharper mind, atoms became more than a whisper. They became a language, a way to describe the universe, one particle at a time. In the snowy heart of 19th century Russia, wrapped in furs and surrounded by stacks of chemical data, Dmitry Mendeleev was doing something unusual for a scientist. He was playing a kind of intellectual solitaire with atoms. It was the late 1860s and chemistry was still a bit of a wild west. Scientists had discovered dozens of elements by now, but the list was messy, an ever-growing collection of substances without clear relationships or structure. It was like owning a dictionary where the words were tossed in at random. And Mendeleev, with his thick beard and sharper-than-average curiosity, decided to bring order to the chaos. Dmitry Ivanovich Mendeleev was no stranger to perseverance. Born in a small Siberian town in 1834, the youngest of at least 14 children, yes, 14, he was raised in the kind of environment that breeds either despair or relentless determination. He chose the latter. After his father lost his sight and passed away, and his mother's glass factory burned down, Mendeleev's mother still managed to get him to university by dragging him across the country. Literally. She took him by horse and carriage from Tobolsk to St. Petersburg so he could enroll in school. As far as supportive parenting goes, that's a hard act to follow. By the time he became a professor, Mendeleev was deeply immersed in the puzzle of chemical elements. More and more were being discovered, but their relationships remained unclear. Some elements behaved similarly to others. Lithium, sodium, and potassium all reacted violently with water, for example. But nobody had found a master key to explain the patterns. Some tried grouping them by atomic weight. Others looked at reactivity. But the arrangements were inconsistent and left a lot of questions hanging. Mendeleev had a different strategy. He approached the problem like a card game. In fact, he used actual cards, one for each known element, on which he wrote the element's properties, atomic weight, chemical behavior, density, and more. Then he shuffled and arranged them over and over, searching for a pattern that made sense. It was like a scientific version of Tetris, only with hydrogen and chlorine instead of blocks. Eventually, a remarkable rhythm began to emerge. Mendeleev noticed that if he arranged the elements in order of increasing atomic weight, certain properties repeated at regular intervals. Soft metals, reactive halogens, noble gases, they all showed up in a kind of musical loop. It was as though the elements were singing in harmony, each voice returning after a predictable number of steps. This led him to construct what would become known as the periodic table, a grid where elements were placed not just by weight, but by their chemical behavior. Elements in the same column or group shared similar properties. Alkali metals formed one family, noble gases another, and the transition metals marched across the center, like a well-trained army. But Mendeleev didn't stop there. He noticed something even more profound. Some elements didn't quite fit the pattern if arranged strictly by atomic weight. Instead of forcing them into awkward spots, he moved them boldly. He swapped elements like tellurium and iodine, even though their weights were out of order because their properties lined up better that way. This was a risky move. It meant trusting the pattern more than the numbers. But it paid off. Most impressively, Mendeleev left deliberate gaps in his table. Empty spaces. These weren't mistakes. They were predictions. He boldly declared that elements should exist in those spaces, even though nobody had discovered them yet. And he didn't just shrug and move on. He described the properties those missing elements would likely have, their weights, densities, oxides, and affinities. One such predicted element, which he called Eka aluminum, Eka meaning one beyond in Sanskrit, would later be discovered and named gallium. Its properties matched Mendeleev's forecast almost perfectly. Another, Eka silicon, turned out to be germanium. One by one, the gaps in his table were filled, not by guesswork or luck, but by the structure he had seen hiding in plain sight. This predictive power gave the periodic table a credibility few scientific models ever achieve. It wasn't just a retrospective summary. It was a forward-looking map of the elemental world. Mendeleev had turned chemistry into a guided tour rather than a scavenger hunt. At first, not everyone was convinced. Many chemists were skeptical of the rearrangements and the empty spaces. But as the predicted elements were discovered and their properties matched the forecasts, Mendeleev's reputation soared. He had done what no one else had managed. He brought a deep and elegant order to the fundamental building blocks of matter. What's particularly charming about Mendeleev's approach is how intuitive it was. He didn't start with a grand theory or a complex formula. He started with index cards, careful observation, and a refusal to give up on the idea that nature must have some kind of logic. He believed the elements were telling a story, and he was determined to listen until he could understand the plot. Of course, Mendeleev wasn't working with the modern understanding of atoms. The concept of protons and electrons hadn't yet been nailed down. He didn't know about atomic number, the count of protons that uniquely identifies each element. That would come later. But his faith in the periodicity of properties was strong enough to override even the official numbers. And when atomic number was eventually discovered, it turned out to explain why the table worked. It wasn't atomic weight that determined placement, but atomic number. And Mendeleev had, through intuition and logic, gotten it mostly right anyway. Beyond his contributions to chemistry, Mendeleev was a bit of a polymath. He worked on everything from oil refining to agricultural reform to the standardization of vodka. He even tried to devise a unified theory of everything, though that part didn't quite pan out. Still, his versatility reflected the same spirit of curiosity that made his table possible. He wanted to understand how things fit together, whether they were atoms, molecules, or economic policies. Mendeleev's periodic table is now taught in every chemistry classroom around the world. It has grown and evolved over time. New elements have been discovered, new rows added, but the bones of his structure remain. It's a rare scientific creation that still stands strong over 150 years after its invention. The table has become not just a reference, but a symbol of scientific order, predictability, and beauty. There's something deeply satisfying about the idea that the universe has a rhythm and that we can learn to hear it. That the elements, those raw ingredients of stars and stones and soup, can be arranged into a coherent pattern that stretches across time and space. Mendeleev didn't just give us a way to memorize chemical facts. He gave us a way to see them, lined up like dancers in a cosmic waltz. And it all started with a game of cards, a stack of notes, and a refusal to accept that nature could be so disorganized. In a world growing more complex by the day, Mendeleev showed that even the smallest pieces can reveal a grand design. If you're willing to look closely, trust your instincts, and maybe shuffle the deck once or twice. By the late 19th century, atoms had settled comfortably into the role of fundamental building blocks, indivisible, solid, and reliable. Dalton had given them mass and identity, and Mendeleev had organized them into a neat table. Chemists and physicists alike were growing rather fond of the idea that the atom was the final stop on the journey inward, a tidy little sphere, behaving itself politely, forming bonds and reactions without too much fuss. And then, zap! Something strange began to flicker out of glass tubes and into the minds of puzzled scientists. A curious, glowing beam, seemingly emerging from nowhere and refusing to follow the rules. These were the cathode rays, and they would crack open the atomic world in ways nobody saw coming. Cathode rays first showed up in experiments with vacuum tubes, sealed glass chambers from which most of the air had been removed. When a high voltage was applied between two metal electrodes inside the tube, a mysterious greenish glow appeared. The glow always seemed to originate from the negative electrode, or cathode, and shoot across the tube in a straight line. These rays could make fluorescent materials light up, cast shadows, and even spin tiny paddle wheels placed in their path. Clearly, they weren't just light. They had momentum. They were something. But what exactly? Some scientists thought the rays were a kind of wave, maybe a strange light wave bouncing around inside the tube. Others suspected they were particles. But if so, particles of what? Atoms were supposed to be indivisible, whole, unbreakable units. What kind of particle could come out of one? Enter Joseph John Thomson, or JJ to his colleagues, a Cambridge physicist with a brilliant mind and a delightfully understated demeanor. Thomson didn't set out to shatter the atomic model. He was just trying to understand the behavior of these curious rays. But, as it often goes in science, a simple question turned into a revolutionary discovery. Thomson's key insight came from bending the rays. He built an apparatus that allowed him to apply electric and magnetic fields to the beam of cathode rays. If the rays were made of charged particles, then the fields should deflect them. And they did beautifully. The rays curved under the influence of the fields, just as a stream of charged bullets would. From the degree of deflection, Thomson was able to calculate something extraordinary: the ratio of the charge of the particles to their mass. And the result was astonishing. These particles were about 2,000 times lighter than a hydrogen atom, the lightest known atom at the time. That meant they couldn't be atoms at all. They were something inside the atom. Something smaller and clearly charged. Thomson had just discovered the electron. It was the first subatomic particle ever identified, and it completely shattered the idea of the atom as indivisible. The solid sphere was no longer so solid. After all, the atom had an inner life, a structure. There were bits within it, and those bits could move. To explain this strange new reality, Thomson proposed a model of the atom that looked, well, a bit like dessert. He imagined the atom as a kind of soft, positively charged sphere, like a cake or a cloud of pudding, with the negatively charged electrons embedded throughout it like raisins. This became known as the plum pudding model, a name that stuck despite sounding like something from a Victorian cookbook. It was a strange image, but it made sense at the time. If atoms were electrically neutral, and now we knew they contained negatively charged electrons, then there had to be some positive charge in there too, to balance things out. Thomson's model pictured this positive charge as a kind of diffuse goo, with the electrons floating in it like fruit in jelly. Not everyone was thrilled about comparing atoms to pudding. But the model had real strengths. J. Thomson's discovery of the electron marked a revolutionary shift in atomic theory. His plum pudding model introduced the idea that atoms had internal structure, challenging the long-held belief that atoms were indivisible. While the model was eventually replaced, it was essential in opening the door to deeper exploration. His experiments with cathode rays showed that atoms weren't solid spheres, but contained smaller, charged particles. This raised new questions. Where was the positive charge? Did electrons move in patterns? Thomson's contributions extended beyond electrons. He also advanced our understanding of ions, isotopes, and mass spectrometry, earning a Nobel Prize and presidency of the Royal Society. His legacy lived on through his student, Ernest Rutherford, who redefined the atom again. Rutherford didn't just change the model of the atom, he transformed how we think about matter itself. His gold foil experiment revealed a world where atoms are mostly empty, their mass concentrated in a tiny, dense nucleus, while electrons orbit in vast spaces like stars in a galaxy. This profound insight laid the foundation for nuclear physics, atomic energy, and our deeper understanding of elemental structure. It turned everyday objects, solid and familiar, into illusionary frameworks of space held together by invisible forces. But the atom's story wasn't over. By the 1930s, scientists realized the atomic nucleus was even more complex. Positively charged protons, packed tightly together, should repel each other, yet they didn't. And atomic masses didn't quite add up. The missing piece? A new, mysterious particle with mass but no charge, a silent partner in the nucleus that would soon be discovered. the neutron. Enter James Chadwick, a quiet and determined British physicist who looked less like a particle smasher and more like someone who might help you find a good book in a quiet library. But make no mistake, Chadwick was on the hunt for a ghost. For years, physicists had speculated that a neutral particle might exist, but proving it had proven elusive. In 1932, Chadwick finally caught it. The breakthrough came when he revisited a puzzling experiment by Frederick and Irene Joliot-Curie, who had bombarded beryllium with alpha particles and noticed that it emitted an unusual, highly penetrating radiation. They assumed it was gamma rays, very high-energy electromagnetic waves. But the energy levels seemed oddly high.
Too high.
Almost suspiciously. So Chadwick suspected something else entirely. What if this wasn't electromagnetic radiation, but a stream of actual particles? Particles that had no electric charge, and yet had enough mass to knock other atoms around? James Chadwick's discovery of the neutron in 1932 completed the picture of the atomic nucleus. Through careful experiments, he identified a particle with mass but no charge, explaining why atomic mass didn't match proton and electron counts alone. Though humble in nature, the neutron turned out to be crucial. It acts like a silent nuclear glue, balancing the repulsion between protons and stabilizing the nucleus through the strong nuclear force. This discovery also unlocked the mystery of isotopes, atoms of the same element with different masses due to varying neutron numbers, like carbon, 12, -13, and -14. Neutrons, uncharged and undeterred by electric fields, became essential tools for probing atoms. They could trigger nuclear fission, unleashing immense energy and enabling nuclear reactors and atomic bombs, marking both progress and peril. Quiet but powerful, the neutron doesn't shine like the electron or crash like the proton, but without it, matter wouldn't hold together. It also plays a major role in cosmic events, like the formation of neutron stars, where unimaginable densities crush atoms into seas of neutrons. Chadwick, a modest man, earned the Nobel Prize in 1935, later joining the Manhattan Project. His discovery, though understated, was transformative, bringing both understanding and new questions. The neutron made the atom complete, and in doing so, opened the door to modern nuclear science. But in the late 1800s, he found himself tangled up in a very non-classical problem, the ultraviolet catastrophe. This was the unsettling prediction that, according to classical theory, a black body, an idealized object that absorbs and emits all frequencies of radiation, should emit infinite energy at ultraviolet and higher frequencies. It began with a mathematical crisis, the ultraviolet catastrophe, where classical physics predicted that warm objects should emit infinite energy. To fix this, Max Planck proposed a daring idea. Light energy comes in discrete packets or quanta defined by what we now call Planck's constant. He didn't know if it was physically real, but the math worked. Then came Einstein, who took Planck's idea seriously and applied it to the photoelectric effect. He proposed that light is made of particles called photons and showed that only high-frequency light could knock electrons loose from metal, not brightness, but frequency mattered. This won him the Nobel Prize and proved light behaves not just like a wave, but like a particle too. But light didn't stop being weird. It could still interfere like a wave, even when sent through a double slit one photon at a time, as if each photon traveled through both slits at once. This gave rise to the mind-bending concept of wave-particle duality. Light, and later, matter, can act as both a wave and a particle, depending on how it's measured. Observation itself became part of the equation. Measuring a quantum system changes it, collapsing a fuzzy wave into a definite state. Reality was no longer absolute. It became probabilistic. And behind it all is light, the universe's most elusive shapeshifter. Sometimes wave, sometimes particle, always traveling at the same constant speed, bending space and time in the process. What started as a puzzle about glowing objects transformed into a radical new framework, quantum mechanics, a world where certainty dies and possibility reigns. It all started with light, the glow of hot metals and mysterious flickers that refused to obey classical physics. Max Planck saved the math by suggesting light came in tiny packets, quanta. Then Einstein declared, "These quanta are real, photons," and used them to explain the photoelectric effect, proving that light was both particle and wave. Enter Niels Bohr, who used light's spectral fingerprints to map electrons orbiting nuclei in quantized energy levels. His atomic model bridged classical intuition with quantum reality and, though later replaced, remains iconic, a stepping stone toward deeper truths. As physicists dug further, reality got fuzzier. Werner Heisenberg introduced the uncertainty principle. The more you know about a particle's position, the less you know about its momentum. Certainty gave way to probability. Nature wasn't broken, just weirder than we imagined. Erwin Schrödinger followed with his famous wave equation, describing particles not as points, but as probability waves. Electrons weren't objects in orbit, but clouds of possibility. Reality didn't exist in definite states until observed. Superposition and measurement became central themes. The revolution didn't stop at theory. These ideas powered technologies: semiconductors, lasers, quantum computers, and even medicine. Radioactive isotopes diagnose and treat diseases. Nanotechnology lets us build structures atom by atom. That's roughly the width of a few atoms placed side by side. At this scale, matter doesn't behave the way you'd expect. Gold, for instance, turns red or purple. Carbon can be transformed into tubes stronger than steel or sheets more conductive than copper. Forces that are negligible in the macroscopic world, like van der Waals interactions or surface tension, become dominant. May your dreams be full of hydrogen and stardust, uncertainty, and wonder. And may you wake tomorrow still asking questions, still listening for the soft hum of the atom beneath everything. Good night from the DODO Scientistry.